Hi, I'm Greg Niemeyer, and today we're going to visit the Advanced Light Source at UC Berkeley. We're going to go see if a physicist named Michael Hummel can explain to us what diffraction is exactly. Let's go. Hello. How you doing? Here we are. We're coming in with the rolling camera.
Have you ever been on a synchrotron?
No.
So why not just give you a just 1 minute overview what the synchrotron is, and then you got the idea what we're doing here. Yeah, so my name is Michael Hummel, and I'm a research scientist on the Lawrence Berkeley National Lab. I'm working on Advanced Light Source, what is a synchrotron in Berkeley. We're right around here, and I'm one of the beamline scientists that is responsible for the beamline here on a synchrotron. So what is basically synchrotron is basically a ring. We see the tunnel is behind the concrete,
Right.
and in the tunnel we have a vacuum pumps where the electrons are going the speed of light.
Yeah.
So electrons are rotating in this huge ring, and they're going speeder and faster to the speed of the light. And how it's possible they go so fast is because we have magnets, and the magnets are keeping the electrons in the rotation, so they're going around. And all the time when they change directions, that means the magnets changing, we call the banding magnets.
Yeah.
So they're banding the direction of the electrons. They all the time give up the light. And therefore you see these pipes, they're coming out.
And that's
You see
where
those?
that's
And
where you catch the light?
That's where we're catching the light. The light's getting more focus with the specific optics like mirrors or monochromators. And on the end of the pipe, there is our experimental hutch where we're working with the light that's come to us.
And there's actually light that's coming off of the electron.
Yes,
And the light is
exactly.
coming off of it because it's going at the speed of light.
Yes,
So this is really one huge research collaboration where you have one central cyclotron that accelerates
Exactly.
the electrons, and
Exactly.
then the beam lines that come off it are dedicated to certain labs.
exactly.
I got it.
Exactly.
All right, so it goes around and everybody has this resource and it's shared, and then everybody gets their benefit off of the resource in a tangential kind of way. This is a beautiful model of collaboration.
It is. Yeah, that's a Sibylus. Our beamline is Sibylus. That's a god of light. So that's how we are called. God.
This is where art and science comes together right here. I have a question. We think that information behaves like waves, but we don't know that much about waves. So I've come here to ask you, what is a wave?
It's basically oscillation and vibrations give out the waves when you don't have the material transfer but the energy transfer. So you can imagine you take the stone and dropping in the water. What you see, the waves are spreading around the place where you drop the stone. So what this is basically the oscillation of the water molecule, but the water is not moving, it's just only oscillating. And that's the energy transfer, it's not the material transfer. That's how I call and define the wave.
Can energy transfer without a medium?
Yes, that's electromagnetic waves, maybe you may pointing on this. When you have not the stone, but you have electron. Let's say your electron start to moving like this. We call it excitated electrons, and give up the waves the similar way as the water was moving. And we call electromagnetic wave in this case that the waves is transferring in a media or in a space.
A wave can travel how far?
They can travel as much as they want. They reflect, they diffract. If you have the space, that means there is no media, there is no material, there is just vacuum. You can travel infinite.
What happens when two waves bump into each other?
That's a good question. Bumping two waves, they collide, or we call them colliding waves. If they are in a phase, they may even come up to so-called diffractions, and that's what we're doing exactly here.
Now, you're using diffraction here to show the shadow of a shape of something that is normally too small to see.
Yes.
Can you tell us about that, how that works?
Very simple explanation. When you diffraction's happening most of the time or all the time when you have a wavelength and obstacle. But if the obstacle is the size of the wavelength, or at least close to that, then you can visualize that diffraction's patterns. So it's diffracting objects need to be the size of the wavelengths. We using here on a cyclotron, we're using the X-rays. That's a very small, high energy, small wavelengths. It's about 0.1 nanometer. And so we can see extremely small particles, like we can even see the atoms.
The visible range is 400 to 700 nanometers.
And we are 0.1 nanometer, exactly.
So you're at 1,000%
1,000
of that, yeah. Can you show us what that looks like when you get the information?
The final experiment, I give you a picture here. I think rather we start from the scratch and take the crystals and put on a beam, and you will see how the diffraction pattern looks like and how do you end up with these nice electron density maps. So what we're doing really, we growing our crystals in such a nice tray. And the crystals are in this tiny, so we can open it. I can show you that. So there's a tiny droplet right here. And in this tiny droplet, there are maybe 10 of crystals of the protein that I'm gonna show you how they can diffract. I had a coffee today, so it's gonna be tough for me, but I'm gonna try my best to loop that crystals and bring to the to the beam line. Okay, I got the crystals, and we go straight here. And so we put it on a goniometer, and when you want to see, it's right here, and we have a liquid nitrogen that is blowing on a crystal. This is basically flash freezing.
That's why
to protect from the X-ray damage. We basically using this cryo protection.
Cryo protection.
Cryo cooling.
Okay. So where is the crystal right now? Do I see it on that monitor?
You see it. Oh, I just need to move it a little bit.
I was wondering, yeah, because we just see this.
Yeah, it's right here. Let's go outside. I will see where the crystal really is. You can see on a monitor outside. So now you see the pin here, or you can see it also here very well. And so using the mouse, we can focus our...
So there's a stepper motor that moves this?
Yeah, and so the size of the beam is like this. Wait a minute, but we're gonna zoom in. So you see nice edges of the crystal. You see it? And that's the size of the beam. You can see the size of the beam also here. You can just rotate that. You see how beautiful it is. And that's the protein, it's not the salt.
Wow.
It's pretty impressive that scientists find a way how to really crystallize this protein and such a good behavior. So first I want to try it, so I shoot it for 1 second and see what's happened. And basically I'm getting collect. And on the screen you may see soon some diffractions. So X-rays are coming now. So you got this diffraction spot right now, right here, and so I will try to make it bigger for you. That you, I will move.
So there you have a regular pattern.
And so what is? Yes, exactly. Now we can make a test again and see, because I want to see the diffraction as farther as possible and the bigger angles as possible, because that's define my resolution of diffraction pattern. And the better resolution is the more details I can see in this electron density map. The more details about, let's say, about this atom can be seen. You see? So that's how you prepare your experiments. And then when you're ready to shoot the whole sets, what I'm talking about rotating the crystals, then you can do it. Okay, you get ready for the data collection. And I basically hit the collect.
Wow, now you really see
now you
different
see,
pattern. Now you see rings.
Now you see the rings, so you see this, the core. So in every second, the diffractions slightly change. Boom. You see, it's moving. Yeah, we are finishing our experiment data collection, and it was done in less than 180 seconds. And now we have the structure of this using our calculation process of Fourier transformation, etc. So from the diffraction spot, we can calculate these so-called electron density maps, okay?
Yes.
And if you take a closer look, this is a crystals of protein DNA complex. If you see this a slightly double helix, I mean this is a double helix, and if you can get closer to it.
Isn't this similar to the kind of thing that Rosalind Franklin wanted to show like in 1954 or so?
1954 exactly, and I'm happy you mentioned that, because all the time when I'm going around and giving talks, I give her big credit for being the first person to crystallize DNA.
Now, did she herself see the double helix in the photograph?
She didn't see that, but I have the talks right here, so if you don't mind, I will show you what you really see.
That's her original photograph.
That's
right?
her original photograph. It wasn't collected in a matter of seconds, okay? It was like hours of collection, because the X-ray source was not as we have right now. And she got this nice photographs of X-ray diffractions. So we can correlate what we have right now with what she had it before. Sometimes the resolution is not really important to the question, and the question was in this case, Watson-Crick, what is the structure? So even this really weak diffraction pattern was good enough for her to get the structure for Watson-Crick, get prediction of. And that model didn't change. I have now 180 images, 180 degree.
Can we look at them as a movie?
We indeed can do it very easily.
Should we put this out
yeah,
of the way?
put it out of the way.
I'm very happy. This is where we get to see the movie.
Look at that, how you rotate a crystal, how the diffraction, basically the pattern change.
Yeah.
And now you take these images, you assign each diffraction spot to the position on the lattice.
So now we know that a wave can reveal the position of an object.
Yes.
And the shape of an object if you add all the little pieces of information together. And that is exactly the metaphor that we're working on, that if I get all your consumer data, for example, and I consider each purchase you make a little density on a map, and if I composite that in a certain way and add time, suddenly I get a shape of what you want. So while each individual transaction doesn't tell me much, the composite of these tells me a very detailed picture of a kind of a consumer shape that you might have. And so all the micro data, pieces of data that are available about us as people can be added up aggregated to a clear picture of what this person is all about.